Welcome back to Wood Engineering. My name is Jeff Barochko from Carleton University, and in this video, we are going to do an example of how to calculate bearing resistance. And this example looks a bit similar to the situation we looked at in a previous video, where we're looking at a beam with some joist bearing on top, and I want to calculate every single resistance for compression perpendicular, that is resistance for compression bearing for this entire assembly. So I'm going to have a number of places that I need to check. For the glulam beam, which is identified as number 1 on the drawing there, I'm going to have to check the bearing of the steel columns onto the beam. I'm going to have to check the bearing of the joists onto the beam. And I'm also going to have to check the squeezing bearing capacity for the area that is at the end, where I have a restraint on one side and a load on the other. And I mean, effectively, the beam doesn't know that there's a support there. All it sees is the load. So I have two loads, 22.5 on the bottom, 15 on the top. And since they're within D, that is the depth of the beam, they're within D of each other, then I need to also consider this case for squeezing. And then once I consider all of those resistances, those are the resistances of the glulam beam itself, I also have to check the resistances of the joists, because as the joists are loading the beam is also loading the joist, so the joist also has an associated bearing resistance, compression perpendicular resistance. So I've given the sizes of these. We basically have 2x6 joists on an 80 by 266 glulam beam, and the steel columns, I've provided the base plate geometry, which is just an 80 millimeter square plate, and we're gonna forge ahead. So in the question here, we're assuming dry conditions and standard term loading. That's just going to reduce our work somewhat. So therefore we know that KD equals 1.0. That's standard duration, loading duration factor, KD. KSCP, which is the service condition factor for bearing, compression perpendicular is what the CP is going to be 1.0. And KT, the treatment factor, is also going to be 1.0. So saving us some work later on. Okay, so the first thing we're going to do is start with calculating all the glulam beam resistances. So that's number 1. Okay, so the first thing we want to do is find out what is the strength of the glulam beam for compression perpendicular. I'm going to find all the parameters first, and then I'm going to plug them into the equation for QR, which we reviewed in the video that was all about the equation for QR. So where am I going to find that glulam beam resistance for compression perpendicular? I'm going to get it from table 7.3. This is a Douglas fir larch 20 FE beam. So if I come over here, I have Douglas fir larch. It's 20 FE, which is this column here. And then I read down to compression perpendicular. And you see I have two different values here. One is for compression face bearing, the other is for tension face bearing. They both happen to be 7.0 here. And this is usually the case that they're the same, but the reason that it's separated is because for hem-fir, they're actually different. And the reason that they're different is because of this issue of the plies on the top and bottom of a glulam being potentially different for the E grades than for the EX grade. So I'll show you that example. If I come over here, hem-fir and Douglas fir larch, which is a separate grade, they're separate species, 20 FE, if I read down, I see compression perpendicular for compression face bearing is 4.6, but for tension face bearing is 7.0. That's because they're using a weaker grade of lumber for the top surface of the glulam beam, for a beam that is only bending in one direction. So here we have 7 for both, so I'm just going to adopt 7.0 as our FCP equals 7.0 MPa. And this is for both tension and compression face. And we get that from table 7.3, which we should be well familiar with by now. Okay, so then I can calculate my capital FCP, which is my modified strength, which, if we recall, is modified by KD, KS, and KT. There's no KH in this equation for compression perpendicular because by definition for bearing, I can only have one element there. I can't have multiple elements sharing a bearing surface. That's just nonsensical. So I end up with 7.0 MPa, and my phi is 0.8, which is just what the phi factor is for bearing resistance. Okay, so we're going to go over these one by one. I'm going to start with the steel column bearing resistance. So I'm going to call that I. Okay, and we're going to start with the effective all applied load check. So this is the local bearing check for loads that are only depressing a certain percentage of the depth of the member, as we discussed in the previous video. And we have to do this check because I have this 22.5 kilonewton load, which is the overall load that is going directly into the support there. Now, a portion of that load obviously is coming from here, but a portion of that load is also coming from number 3, right, which is transferred through the beam through shear, and then gets changed in direction to go in compression perpendicular once it gets to the support. But there is a total load there that needs to be resisted. So I use that total load and I look for just the local compression, and then later we're going to check the squeezing, and we're going to check that only against this portion of the load, the portion of the load that goes between the top and bottom of the beam. So right now I'm going to check against the total load. That's why it's called effective all applied loads. And we will recall the equation for that is phi capital FCP AB, which is the bearing area, KB, which is the bearing factor, length of bearing factor, and KZCP, which is the size effect factor. And we're going to go through what each of these parameters is. So AB, the bearing surface, is just the surface that interacts between the column and the beam. So this beam is 80 millimeters wide. It's an 80 by 266. I haven't identified that the height is the 266. I can do that explicitly, but I mean, if I saw this in a drawing, I would assume that since this is a beam, we would arrange it in the strong axis direction for bending. I mean, we're not going to take a beam like this and put it flat, likely, if we're trying to use that beam to resist bending. So it's the up and down direction, which is the 266. And so the beam is 80 millimeters wide. The plate is also 80 millimeters wide. It's 80 by 80. And so the interaction surfaces between the two is 80 by 80. Now, if the piece of wood was skinnier than that plate, then it would only be the portion of the wood that's actually sitting on the plate that would be the bearing surface. So let's say, if that Glulam beam was only, 50 millimeters wide, for example, sitting on an 80 millimeter plate, part of that plate doesn't have any wood on it, so there's no bearing happening there. So it would only be the portion, the 50 portion of the width, times the length, which would still be 80 in this case, that would be the bearing area. But in this case, the plate is just as wide as the beam exactly. So our bearing area is the same size as the plate, which is 80 by 80 millimeters, which comes out to 6,400 millimeters squared. Okay, now, what about our KB? That's our length of bearing factor. So our bearing length is 80, which is certainly less than the values that are shown in the table. So here's the KB table, length of bearing factor table. You can see that for 80, I would potentially have a length of bearing factor, KB, that is greater than 1. But I need to recall that this table only applies if A, I'm not near the end of a member, not within 75 millimeters of the end of a member, and B, that I'm not in an area of high bending stress. So here in particular, I'm definitely within 75 millimeters of the end. The joist is basically right at the end of the member. I haven't specifically shown that it's within 75 millimeters, but let's say that it is. So therefore, KB has to be 1.0 because it's within 75 millimeters of the member end. Okay, then what about KZCP? I'm going to move down for this because I want to draw a picture. So just to remind you what this looks like, I'm showing a cross section now of the beam. So it's like I'm looking at the end of the beam from the left, for example. So here I'm looking at the left side of the beam, looking this way. So I can see the glulam, and the glulam is made of smaller pieces. all glued together like this, as we've seen before. And so we recall that size effect factor is to account for the ring orientation on the piece. And if we're loading on the flat, basically, of a piece of wood, we're less likely to get the worst case ring orientation in the entire bearing surface. So for that reason, we are not considering the full size of the beam when calculating KZCP. We're going to use just one lamination. And you will recall that this is the table for size effect factor. And so based on the ratio of member width to member depth, I get to maybe consider KZCP to increase the strength. Now in this case, the width is 80, but the depth that I'm considering is just the depth of this lamination, because that's the size of the piece that affects the way that the grain is oriented. So I'm going to assume, and this is an assumption we will continue to make, and it's not always the case, but in the absence here of actual data about exactly what the lamination sizes are, we will assume that the lamination thickness is 38 millimeters, which is the same thickness as a 2x, right? It's like 1.5 inches. So that's the number that we're going to use when we calculate the width to depth ratio in order to determine our size effect factor. So width to depth in this case is 80 divided by 38, which equals 2.1. So therefore our KZCP equals, it's 2.0 or more. So therefore our KZCP equals 1.15. Beautiful. Okay, so now I have all my pieces for my equation, so I can go ahead back and sub back in for the effect of all applied loads equation. That's my phi times my strength times my area times KB was 1 and KZCP is 1.15, and if I multiply that out, I get 41.2 kilonewtons. Okay, so now which applied load am I going to compare this resistance to? I'm looking at effect of all applied loads at the steel column, which is this area right here. Therefore, I'm comparing to the total load that is on the column. So whenever I'm using the effect of all applied loads resistance, QR, I'm comparing it to whatever is the local total bearing load at that location. So in this case, that is 22.5. So when I do that, I see that my QF is quite a bit lower than my QR, so everything is fine. So QR is greater than QF. Very good. Okay, so now we're going to move on and talk about the joist bearing on the beam, joist number 2, which is the one at the left identified by the purple 2. So again, I'm going to start with the effect of all applied loads check, which is the same one that we just did, which is looking at just the local bearing capacity, not considering the effect of squeezing the beam. Okay, so again here, KB is equal to 1.0 because we're still within 75 millimeters. Okay, and KZCP is still equal to 1.15 because now we're talking about the top surface instead of the bottom, but the Glulam top lamination geometry stays the same. That's not how you spell lamination, nor is that a proper M. Lamination as above, so same as what we did before. Okay, and our AB in this case is the intersection between the two. So now we're talking about this joist number 2, which is right near the end, and we're looking at this surface here. So that surface is the same width as the joist, which is 38, because that's a 38 by 140 joist. And in and out of the plane, it's the width of the beam, because we're told that those joists are continuous over top of the beam, which is the note I've given on the left. So it's 38 by 80. And once I sub all that in to my equation for QR, the effect of all applied loads bearing resistance equation, I get 19.6, which you'll notice is quite a bit less than last time. Last time was 41.2. Why? Because the bearing surface is now much smaller. It used to be 80 by 80, now it's only 38 by 80. And I'm going to compare that to the applied load, which for that member is QF equals 15 kilonewtons. That's how much load that joist is applying to the top surface of the beam. So still, it's a bit smaller resistance, but still QR is greater than QF, so we do not have a problem. So that's okay. Okay, so next I'm going to check the effect of squeezing between those two. So since I have two loads on either side of the member, I have the 22.5 on the bottom and I have the 15 on the top. Right at the end of the beam over here, in between those two, I have stress perpendicular to grain that goes all the way through the depth of the beam. So instead of just being near the surface of the beam and then eventually being transferred to shear to move elsewhere to get to supports, here it goes directly all the way through the beam, which means we have a longer length to strain, which means that for a given force, we're going to have a larger total deformation. So given force, same stress, same strain, but since we have a longer length, we have a more deformation. And you recall from the other video that compression perpendicular strength design in wood is actually a deflection criteria, kind of reformulated into a strength criteria. So in order to do that, I'm going to use the other equation. So now I'm doing the effect of loads applied near a support, which I've been colloquially calling the squeezing load case, or the squeezing resistance case rather. And it has a slightly different equation. Since the load is going all the way through the member and I'm going to get larger deformation at the surface for the same amount of stress, we apply this factor 2/3 to reduce the apparent strength. The rest of the equation is largely the same, except I now have an AB prime instead of AB, and that takes into account the fact that I now have two bearing surfaces instead of just the one. So let's calculate our AB prime, okay, which uses this equation. It's basically a average of the two, as we've seen. So B is an average bearing width, and LB1 plus LB2 over 2 is an average bearing length. And we have a limit so that we cannot take unfair advantage of a small width by just balancing it by an extra large width on the other side. So here our B is, remember our B on the top was 80, our B on the bottom was 80, that's our bearing width, because both of them are on the full width of the beam. So I have 80 plus 80 over 2, which transparently is equal to 80. No need really even to do that calculation. And I have a length of bearing 1, which is always the shorter bearing length. Okay, it's not like this one's the top and this one's the bottom. LB1 is always less than LB2. Remember, on the top, I have 38 millimeters because that's the width of the joist. And on the bottom, I had 80 millimeters because that's the length of the plate. So this one is always the lesser. Okay, so when I do that calculation, I get a value of 4720 as my average bearing area, which is just, I mean, I would get the same number if I just took if I found the area of the top and the area of the bottom and I just took the average of the two. But it has to be less than this value of 1.5 times 80 times 38, which is 1.5 times the average bearing width times the lesser bearing length. And for that number, I get 4560. So 4560 is smaller. This is one of those cases where the number is a cap. Doesn't mean I have to change my design, but it does mean that I have to consider that AB prime is 4560, which is the lower number out of those two. So I'm only allowed to consider 4560. So there's some area of my longer bearing length that I'm just considering as not even there for the purposes of calculating the squeezing bearing resistance, the effective loads applied near a support. Okay, so now KB is 1.0. Why? Because we are still within 75 millimeters of the end. And our size effect factor is still 1.15 because we're still talking about the Glulam laminations on either side. There is one other requirement, which is that when I'm figuring out which FCP to use, it's obvious in the effect of all applied loads which FCP to use, because I just use whichever side I'm applying the load. So I either use the bottom one, the compression face, or the top one. Sorry, the other way around. The bottom one would typically be the tension face, and the top one would typically be the compression face. I mean, unless you're continuous over support, obviously. But anyway, I would usually just use whichever strength for the face that I am applying to. But in this case, obviously, I have two faces. So which FCP do I use? I use the compression face one. And the reason is because that's the lower bound of the two. But as we saw in the table 7.3, for most grades of Glulam, those numbers are the same. So that's the case in this case. So it's 7.0 MPa, same as it was before. So then my capital FCP is still 7.0 FPa. So now I can go back to my QR prime equation and sub in the values. Okay, so my QR prime value here, 2/3 0.87 times the area times the KB times the KZCP, I get 19.6. This happens to be the same number that we got for the QR for the joist that we just did. That is a coincidence in this case because we limited our bearing area to 1.5 times the bearing width times the length of the bearing surface at the top, which is the joist, right? And so if I take 1.5 times that, and then if I multiply that by 2/3, then I'm going to get the same answer as I did before. So usually these numbers will not necessarily be the same, but in this case they are. So then which QF do I compare this to? This is the real trick of understanding the way to do this. Okay, so I'm saying here, we're going to compare this resistance to the applied load that goes all the way through the depth. Why am I doing that? So here, remember I have some portion of the load that goes off to 3, and I have some portion of the load that goes directly to 2 here. And it is this portion of the total load that goes between the steel column and the joist number 2 directly. That is the load that's causing the squeezing, right? So 15 kilonewtons from joist 2 goes directly to support, to the steel column support. So 15 kilonewtons out of that 22.5 are directly from the joist. The rest, the 7.5 kilonewtons that are remaining, are coming over from joist number 3, right? Which half of it goes one way and half of it goes the other. So it's only the 15 kilonewton portion at the left end of the beam, the portion that goes all the way through the beam from top to bottom, the 15 kilonewtons, that's the load that's causing the squeezing. So that's the load we use to check against when we find what the squeezing resistance is. So in this case, that's 15 kilonewtons. So that's why I said here, compare the applied load that goes all the way through the depth. And so therefore the QF is 15. And we find that our I'm going to call that QF prime actually, because that's the squeezing load. And QR prime is greater than QF prime. Therefore we're okay. All right, we have one more load to check the beam against. I mean, this is a long process because we have multiple bearing surfaces and we have multiple members to check those bearing surfaces against. So the last one for the beam resistance checks is at joist 3. And to remind you, joist 3 is the one that's towards the center of the beam. Okay. So at joist 3, effect of all applied loads. Okay, so there's no squeezing here because the load is just going off to the side. There's no, at the point of application of joist 3, there's no member on the other side or any other force on the bottom of the beam that is within D, the depth of the beam, from the location of 3 along the beam. So we only have to check the effect of all applied loads, which is the direct bearing check. And so how are we going to calculate KB? So this is the same joist. It's 38 millimeters wide. So really there should be potentially a KB factor because it's a short bearing length. But does it satisfy both categories? Okay. One is is it within 75 millimeters from the end of either of the beam? Okay, it's not. It's near the middle, so I think we can safely say that that's not the case. The second one is the joist in an area of high bending stress for the beam? And that is something that you need to determine based on your own discretion. So you should assess how high the bending stresses of the beam are. Now, this looks like a really chunky beam for not very big joists. So the loads are probably not very high. You know, maybe I'm only within, 10-15% of the total bending resistance or something of this joist. You know, if that's the case, then maybe I'm not in an area of high bending stress. But typically, if I was applying a load at the middle of a beam that's bending, of a bending beam, then that is the area of the beam where the bending stresses are highest. So if I assume that the beam is probably designed for strength or moment at the center, then usually within maybe the middle third of a beam or something like that, those are probably the areas where we do have high bending stresses. But in this case, I'm going to assume that it's not in an area of high bending stress. The reason being just so that I can show an example of getting the proper KB from the table. So let's assume for now that these loads on the beam are very low relative to the beam's moment capacity. So therefore, there are no regions of high bending stress. Okay, which would not generally probably be the best assumption. I'm just going to make a note here. So let's say for now then that the beam is over-designed, as we said. So I'm going to consider the bending stress is low, so we can apply the bearing strength, the length of bearing factor from table 6.5.7.5. So which one am I going to use here? Well, the bearing length for the joist on the beam is 38 millimeters, right? That's the length of the bearing area along the length of the beam, okay? Because that's the width of the joist. So I come to this table and I find 38, and I find that the modification factor KB is 1.25. If I had a value that was in between these numbers, then I could interpolate, I could linearly interpolate between these resulting modification factors. So bearing length is 38 millimeters. And again, we're looking at the joist bearing on the beam. Therefore, our KB is 1.25. And as for our size effect factor, KZCP, this is still going to be 1.15 because we're still talking about bearing on the Glulam top lamination. So the aspect ratio of that lamination remains the same. Okay, so now I can calculate my AB, which is the same as what the AB was for the joist that was bearing at the end on the beam, joist 2, and we get 3040 millimeters squared, and then I can calculate my QR, effective all applied loads. Okay, and when I do that, and the major thing that's changed here relative to the joist that I did at the end of the beam is the KB factor of 1.25. So this value QR is 1.25 greater than the 19.6 that we got previously. And I'm going to compare that to the actual load being applied by that joist, which was 15 kilonewtons. And QR is greater than QF, so I'm good to go. Okay, so those are all the bearing checks for the beam. So the beam is done. But now we have to get to the joists. Because as the joist pushes on the beam pushes on the joist. So the joist has a bearing resistance as well. So we have to do that separately. Okay, so now that we're talking about the joist strength, I have to find the actual strength of the joists for compression perpendicular. And that will be potentially different than what the strength was for the Glulam beam. Okay, so now the strength of the joist itself is going to come into play. This thing. Okay, so let's go to figure out first the grade category for this piece. It's a 38 by 140, which is a 2x6. So 38 by 140 is going to fit, into our structural joist and plank category here. So we have to go to the structural joist and plank table, which happens to be table A, which says structural joist and plank at the top. And you may recall that we were dealing with a Douglas fir number 1 for our joist. And so if we read across, we'll see perpendicular to grain strength FCP equals 7.0. It happens to be the same actually, but this number came from a totally different table. So it would be much more likely to not be the same, but in this case just happens to be the same. Probably that's the case because both of these are made of Douglas fir, and Douglas fir number 1 or number 2 or select are probably the pieces of wood that went into making up the piece of glulam. So they're both made out of the same wood. So this is not really a mystery. 6.3.1a is where we got that value. And so our capital FCP, just like before, KD and KSCP and KT are still 1. So we're dealing with the same conditions. So our capital FCP is the same as our small FCP, and our phi is still 0.8. Okay, so now we can check our effect of all applied loads. And the nice thing here is you'll notice that I combined 2 and 3 joint resistances because these are actually the same bearing surface. Okay, so if we're looking at the resistance on the joint here and here, okay, so actually I should probably have drawn that on the joist itself. So if I'm checking the resistance of this joist and this joist from a load coming here, both of these loads are 15 kilonewtons, right? And the joists are identical, so I have the same load on the same joist with the same geometry, so I only have to check the resistance of that once. Okay, so let's go back and check that. So at least I'm saving some work somewhere. Okay, so we're doing the effect of all applied loads check, which is a regular QR check, not QR prime, because we don't have any squeezing of the joist, right? At the joist, there's only one load, so I don't have to check squeezing there. The joist is continuous over the beam, it said. So basically what I mean is, if this is if I'm looking at the cross section of the beam and my joist is sitting on top, then my joist comes all the way over the top of the beam. So now, we can ask the question, is this within 75 millimeters of the end? Well, if I look at it from the point of view of the beam, yeah, maybe this thing is at the end of the beam, right? So for calculation of KB of the beam, I don't have 75 millimeters over here. But from the point of view of the joist, because now I'm checking the joist strength, if this joist is continuous over the beam, then that means likely I am not within 75 millimeters of the end because this joist continues. Okay, so for that reason, I could consider KB. My other criteria being the high bending stress. I'm going to say for now that it's not because I just want to calculate a KB for the example. But if I did have a situation like this where the joist was going over the top of a beam, then probably this is an area of high bending stress because there would be a peak negative bending moment at this location at this section of the beam, right? Because it's going to be bending down this way and down this way. So probably I shouldn't consider KB, but I'm going to do it anyway just for purposes of the example. So I'm going to consider my bearing length. Okay, and this is the bearing length of the beam on the joist. So it's different than the bearing length that we calculated before. Okay, what is the bearing length of the beam on the joist? Of the joist on the beam. This is what we did before, right? Joist on the beam. The bearing length was 38. Now I'm looking at the effect of the beam on the joist. This is actually, these are approximately the same size as the members that we're using here, except that it would be a 2x6 instead of a 2x4. The bearing length of the beam pushing up on the joist goes along a bearing surface this long, right? This long along the length of the joist. So that's 80 millimeters in our case. So that's the number I'm going to use. Okay, so then if I go to my table for KB, you'll see that for 80 millimeters, I don't actually have a value here. So I'm going to have to interpolate between 1.13 and 1.10 based on where 80 lies between 75 and 100. So let's go ahead and do that. So I'm going to interpolate. Because there's not actually that much difference between these two numbers. I'm going to end up like probably pretty close to 1.13, right? Because I got 80. But I'm going to go through the process anyway, just so that you can see how I would do it. Okay, so what's the difference between 75 and 100? It's 25. And I'm at 80, which is 5 away from 75. So I have 5 over 25. If you don't understand this process, figure it out yourself from scratch. And you should be able to figure it out just by kind of drawing a line between those 2 points. So I'm basically finding out how far I am within that range away from 75. So I know I'm 5 away from 75, and that in the overall length of that space between 75 and 100 is 5/25 or 1/5. So I'm 1/5 of the way between 75 and 100. So I need to find a number that's 1/5 the way between 1.13 and 1.10. So I find what the difference is between 1.13 and 1.10 and take 1/5 of that, which gives me 0.006, which is a very small number. And then I can move myself 0.06 away from 1.13, and I will find an appropriate KB value. 0.006. And I get about, I'm going to get 1.124, right? So I'm going to round that to 1.12. And for KZCP now, my size effect factor, now I'm dealing with the joist, right? And the joist is oriented like this, not like this, which were the laminations in the beam. So the joist is like this. So therefore I need to find the width over depth ratio of this. Width is 38, depth is 140 in our case. Okay, so then I can go to the length of bearing factor table, and you'll see like 38 over 140 is definitely going to be less than 1. So my KZCP is going to be 1. Basically, if I know that my member is arranged vertically like this, with the strong axis up and down with respect to the bearing surface, then my KZCP is going to equal 1. The point of KZCP is to account for members that are being bared against on the long side, on the flat side. So KZCP is going to equal 1.0, right? Because width divided by depth equals 38 divided by 140, which is definitely less than 1.0. Okay, and now what's my area? My bearing area is the same as it was when I was bearing from the joist onto the beam. It's 38 by 80, 3040 millimeters squared. And then I can do my final QR calculation. So I do my QR calculation, I plug in the values that I just determined, I get 19.1 kilonewtons. The load that the beam applies to the joist is the same as the load that the joist applies to the beam, which is 15 kilonewtons. So I check that QR is greater than QF, and it is, and therefore I'm okay. So now by this point, I have checked every single resistance in that assembly. All the resistances of the beam and the resistances of the joists that are sitting on top of the beam. And so hopefully that gives enough varied examples that we can see all of the different things that we might run into when calculate bearing resistances.